Hello and welcome to Unit 3 Solutions, Lecture C, Molarity and Parts per Million. Get your notes, get your reference tables, and get your calculator because today's lecture is pretty much nothing but math. Alright, I told you we were going to measure concentration quantitatively. It's chemistry. We like to know how much. We like to be able to give instructions to other people so they can repeat our data, our lab work, using the same concentration solutions that we did. So we have to have ways of measuring that. The most popular way is going to be something called molarity. And I want you to look at that word closely and pay attention because molarity and moles are not the same thing. Molarity, a derived unit, the unit that we use for it is the capital M, and it has to be capital because a lowercase m is going to be for mass or meters. It's derived by moles of solute per, remember per means divided, liters of solution. Notice it's not of solvent, it's of solution. It's of the total amount you have at the end. That's going to be important in lab when you're mixing up solutions itself. There's a slight difference between you add 1 liter of solvent or you add enough water to make 1 liter of solution. And it mostly becomes important when you use really concentrated solutions with high molarities. When you see a 1 capital M, you read that as 1 molar, 1 molar, and molar is different than moles. Molar means molarity, and that means that you have 1 mole of solute per every liter of solution. If it's 3 capital M, that means you have 3 moles of solute per every liter of solution. 3 moles of solute, more pieces, means that this guy, 3 molar, is more concentrated than the 1 molar one. And again, molar, molarity, those are going to be the same measurement. Moles, either M-O-L or M-O-L-E, are going to be the same thing, and that's a different amount. So right now, get out reference table T, and let's look at the equations. We're going to zoom in here a little bit on just 2 equations here. We have a box for mole calculations. Mole, M-O-L-E, not molarity, but mole. This is moles are going to be the mass of the compound that you're given divided by their gram formula mass. Molarity down here is part of concentration. So within the concentration we have molarity, and that's going to be moles of solute from our equation up there divided by liters of solution. Moles of solute, liters of solution. Both equations are here. Remember, molarity, moles, not the same thing. Molarity, concentration, it's going to be symbolized with a capital M. Moles, shorthanded, M-O-L, divided by liters. Alright, the rest of it is simply plugging in numbers. So once you know that that's a concentration and it's telling you how many moles in a given volume, the rest of it is just math. So the question says, how many moles of solute would 3 liters of a 2 molar solution contain? Remember, I want you to look for these. I want you to use a little chart. They want to know moles. We have liters. They have a molarity. When you look at table T, you're like, oh, look, molarity, moles, and liters. I have 2 of those 3 things. That's the equation that I'm using. So you just have to plug the numbers in. 2 molar equals X over 3 liters. Don't even need our calculator. X is 6 moles. Sometimes your concentration questions are just that easy. Now let's look at the next one. They want to know how many grams of KOH are needed to prepare 250 milliliters of a 2 molar solution. So they want to know grams of KOH. They have 250 milliliters of their solution, and it's 2 molar. Now you know it has something to do with molarity because you see the capital M. But we don't have moles and we don't have liters. So it makes the question a little more difficult. First thing we can do, and the easiest one to solve, is this. We can change milliliters into liters. So 250 milliliters is 0.25 liters. Do not forget to change this to liters. It has to be liters down there in the denominator. You can't use any other volume measurement. To convert grams into moles, they gave us this thing, this formula mass. And it seems like if they gave us this number, we should maybe use it for something. This is how we're going to switch moles into grams. Because when I look over here, I have a molarity and I have a liters. What I don't have are the moles. So I can use this equation. I have a molarity, that's 2. I have a liters now, that's 0.25. And that's going to give me a certain number of moles. So to solve for that, 2 times 0.25, and I have 0.5. And remember that your units then were moles. How do I switch moles to grams? We've got two choices. We can use our factor label. It says it's 56 grams per mole. So I just multiply this by 56. The moles cancel. And half of 56 gives me 28. Or you can go to table T and look at this mole calculation equation where it says moles equals your given mass divided by the formula mass. So moles would equal, let me switch colors. The other way you could do this is use the equation from table T, where moles equals your given mass divided by the gram formula mass. In this case, we have moles as 0.5. Our given mass is what we're looking for, and our gram formula mass is 56. So again, we have 56 times 0.5 to solve for that, and we're going to be right back at 48 grams. Next problem is another straightforward word problem. How many liters? They want to know liters of a 0.5 molar NaOH solution, so capital M, would contain 2 moles of solute. So that's great. Out of my molarity equation, I have 2 of the 3 pieces. I don't even have to do any conversions. 0.5 equals 2 over x. The only thing you have to be careful of here is people automatically want to say that this is 1, but you have to watch your algebra. So we got to get that x out of the denominator first. So what I really have is 0.5x equals 2. So I'm not multiplying by 0.5, I'm actually dividing by 0.5. So remember here, I have 2 divided by 0.5, which is going to be 4, which is a much different answer. And your units, which one were you missing? You were missing the liters at the bottom, so it's 4 liters. Watch out for the algebra. You don't want to set the equation up right and lose the point because of your algebra. You've been doing algebra for a long time. You can do this. Multiple choice questions that you might see with the molarity equation. Which solution is the most concentrated? When you look really quick, you really can't tell. What they're asking you here is what is the molarity of all of these solutions? And molarity is moles divided by liters. So they have this set up really nice. All I have to do is divide. 1 mole divided by 1 liter is 1 molar. 2 moles divided by 1 liter is 2 molar. 6 moles divided by 10 liters is 0.6 molar. And 4 moles divided by 8 liters is 0.5 molar. So our most concentrated is going to be the 2 molar solution. All right, there's another equation that involves molarity on your reference table, and it's not always obvious that we can use it for these concentration problems because the box that it is listed under says titration. So let's take a look at that on table T. Down here, titration. Titration is going to be a special lab technique that we'll use for acids and bases. So when you look at this equation, they have these little A's and B's down here. So it's the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. But we can also use this if we're just diluting down a concentration, or we're letting the water evaporate and we're increasing the concentration of a solution. Just ignore the A's and B's. Think of them as ones and twos like we did for the combined gas law. So we can just have our starting solution and our ending solution. So think of it as M1V1 equals M2V2, and we're all set. So sample questions. When 20 milliliters of a 1 molar, there should be a capital M in there, a 1 molar HCl solution is diluted to a volume of 50 milliliters. So I have 20 milliliters of a 1 molar solution, and we're going to dilute it down to a volume of 50 milliliters. What is the new concentration? So I can just use MV equals MV. 20 times 1 equals 50 times X. 20 divided by 50, and we have a 0.4, and now the units that we used, this was a volume, it was the milliliters, so that's your molarity. And it's as simple as that. Next problem. 100 milliliters of a 1 molar solution of KF is evaporated down until it has a volume of 25 milliliters. What is the new concentration? Again, we're using milliliters. You don't have to convert that volume into liters as long as both of these are milliliters. Because of the math that we're doing, the units will cancel out. So I have 100 times 1 equals 25 times X, and our answer is 4, and the units molars. And see if it makes sense. If I'm diluting this down, it should get weaker. 0.4 is weaker than 1. If I'm concentrating this out by evaporating, so I'm making it more concentrated, I'm getting rid of the water, my molarity should go up. 4 is higher than 1, it goes up. So I've done my math correctly. We use molarity for solutions that are pretty soluble in water, but we're going to have some compounds that barely dissolve in water at all, and some of them, even at very small amounts, become very important to know how much is in there. Usually in environmental science, hopefully some of you will be environmental chemists and you'll help clean up the environment. You're going to want to know about parts per million, and there they even do parts per billion. So things like lead and mercury and some of these other chlorinated compounds, even in small amounts in our water, are bad for us. So parts per million is exactly that. They're saying if I have 1 million particles, how many of those parts would be my target solute? And the equation for it's on table T. It's in the same concentration box as our molarity. It's right here, parts per million. You're going to use this for things that are only slightly soluble. They're very low concentrations, typically things that you can't see or smell, or you wouldn't even know that they're there, but they are. So when you read the equations, you just have to figure out which is the solute and know that you're using grams of solution. Here is where you have to remember that the density of water is 1. So 1 milliliter of water has a mass of 1 gram. So if they have a liter of solution, that's 1,000 grams. If you have 250 milliliters of solution, that's 250 grams. If you have 3 liters of solution, that's 3,000 grams. You have to know that relationship between volume of water and grams of water, because odds are they're going to give you the volume of solution instead of the number of grams. Very simple. You just take your grams of solute, put it over grams of solution, multiply it by 1 million. The biggest mistake students make is canceling out these zeros or plugging those zeros in later. Just be really careful. Clear your calculator. Do it a couple of times. One of the things that you'll notice is you're going to start to see these square brackets as shorthand. When you see the square brackets, that means the concentration of. So square brackets are concentration. They want to know the concentration of NaCl, square brackets, NaCl. That's what the shorthand means. And we'll just do practice problems with parts per million in class. The math itself is pretty straightforward. The questions themselves also pretty straightforward.